This is a video going over Geometry Semester A, Unit 4, Course Activity Triangle Similarity. The actual activity starts on page 5, where it says Task 1, AA, standing for angle, angle, criterion for similar triangles. What it's asking us to do is to use GeoGebra to investigate whether two pairs of corresponding angles in two triangles are enough to prove that the two triangles are similar. So we are going to use GeoGebra to complete the activity and see if the triangles that we create are similar. So I'm going to start with task 1. Task 1 tells us to create a random triangle ABC. That's easy enough to do, so I'm going to go ahead and click on the Polygon tab in GeoGebra, click where it says Polygon, and I am going to create a triangle by clicking 3 different points. I'm going to click here, here, and here, and this creates my random triangle. Once I click my third point, however, I'm going to link it back with my first point, and that's going to create our random triangle. Part A also asks us to measure and record its angles. So I'm going to click on the Measure tab. I'm going to click where it says Angle, and I'm going to click in the center of the triangle, and that gives us our angle length for each of the angles in our random triangle. I'm going to record these and put them in the unit activity, and that completes part A. Part B is where it starts getting a little bit more involved. It asks us to attempt to copy our original triangle using 2 of its angles. So we do that by first drawing a new line segment DE parallel to our line AB. So I'm going to choose the line relation tab on GeoGebra. I'm going to click on line AB, and it creates a parallel line to that original line. And I want my point D to line up with my point A. So I'm going to click here, creating my point D on the same line. So I have my point D, but I want my line segment DE. So I'm going to go along the parallel line, and I don't want my point E to line up with my point B. They need to be different from one another. From there, it asks me to create from point D, an angle with the same measure as CAB. So recreate angle A essentially. So I'm going to go to my Measure tab, and I'm going to create an angle with a given size. So I click E, D, and I'm going to input my desired angle, which is 75.96. And I want it to be clockwise from the line. And that creates our desired angle. I'm going to do something very similar to point E, where I recreate, it's supposed to be with a given size. I'm going to recreate angle B, where angle E is here. So I'm going to go 59.04, and I want it to go counterclockwise. And now I have my 2 angle measures. From here, I need to create a ray from E and a ray from D, so when they intersect, they create a third point. So I'm going to get my ray tool. I'm going to line it up with the angle I created, like so. And I'm going to do the same thing here. I'm going to create a ray and have it line up like so. I don't want to click my point F quite yet, because that point F is going to go right here, where the 2 lines intersect. From here, I am going to create my new triangle DEF, and I'm going to record its angle lengths. So once again, I'm going to go to my Measure tool where it clicks Angle. I'm going to click inside this triangle, and it gives me, we had our two original angles, but we get our final angle, F, which is equal to C. And I'm going to record that in Edmentum. Part C asks us to compare the shapes and angle measures of triangle ABC and triangle DEF. So, looking at the triangles, the angles are equal to one another. They have corresponding angles. A corresponds to D, B corresponds to E, and C corresponds to F. So the angles are equal in both triangles. But triangle ABC is a little bit bigger than DEF. And we could verify this by clicking the measure tool on distance and clicking this line here and this line here. So the angles are different, the size is different, but the shapes, they look pretty similar to one another. So you would put something to that effect for part C. Part D asks us to find the ratio between sides DE and sides AB. A ratio is a comparison between two numbers or two measurements. So I'm going to set up my ratio AB. So for AB, I'm going to write 4.12 because that's its length over the length of DE, that being 3.44. And as I plug that into my calculator, I get the number 1.19767, and then it goes on for a while. So what this number means is that angle or triangle ABC is 1.19767 times as big as triangle DEF. So this is our ratio, this is our comparison between the two. So you would record that for part D. You really only need to put the first couple of numbers. You could round to 1.2, but for our next part, you want to keep as many of these numbers as possible, and you're going to see why in a moment. So part E asks us to dilate triangle ABC centered at the origin using the scale factor n from part D. And using GeoGebra, there's not really a convenient way to do that, but I could boil down what it's asking you to do, and you kind of see how they compare. So first thing I want to do is I want to record the side lengths for all parts of our both triangles. So we have 4.12, 5.66, and 5 for ABC, and 3.44, 4.72, and 4.18 for our triangle DEF. And what the question is really asking is, can I transform or multiply the side lengths of one triangle into the other triangle using the ratio? And the answer is yes. Yes, I can. And the way I would do that is by taking the side lengths of DEF, so 3.44, 4.72, and 4.18, and multiply all of them by our ratio. And again, our ratio is going to be 1.1976. And again, you don't want to cut that off, but I'm just not going to write every single number here. So you're going to multiply each of those side lengths by our ratio, and what you should get is our new DE is equal to 4.12. Our new EF should be equal to 5.66. And our new DF should be equal to 5. You're going to probably need some rounding for this one. That being said, this completes your part E. Just record the new side lengths for our new modified DEF and our ABC. So part F asks us, what can you conclude about triangle ABC and DEF based on their side length and angle measures? Well, if we scroll back to the top and look at the title, it says angle criterion for similar triangles. So we were trying to figure out what we could tell about two triangles if we're given two sets of equal angles. And the answer is, well, we could determine that if there are two triangles that have two equal angles, that means that the third angle must also be equal. And furthermore, they have corresponding sides. And you could dilate one triangle so that the side lengths are equal to the other triangle. So you could transform one triangle to equal exactly the other triangle, which means that if you have two angles that are the same or shared between two triangles, that means that the triangles are similar. And if the side lengths are equal, then they are congruent. So that is the long and short of what we have proved here. I've sort of spoke on part F and part G together. Part F, all they're really asking for you to state is that, yes, the two triangles are equal when you dilate one of them. And part G is that you can use angle criterion to establish that if there are two triangles that have two angles that are equal, then the triangles must be similar.